Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. Now, there's still a few people coming in at the moment, so I'm going to spend the first couple of minutes talking you through the software we're using and how you can use that to interact with our guest speakers today. Then I'll let you know a little bit more about what's coming up. We then have two recorded presentations, so you can sit back and enjoy those, after which we'll go to Q&A, live Q&A with our guests. So the most important thing that you need to know over the course of the next hour is how you can ask questions of our guests. And the simple way to do that is using the GoToWebinar panel. Now that should be a box probably floating on the right hand side of your screen. You can move that around, put it wherever you need it, minimize it. But at the bottom of that is a section where you can ask questions. And any questions that you have about the topic, about the content as it comes in, just put them all straight into that box and we will pick them up as we go throughout the presentations and then into the Q&A at the end. If there's any part of this that you miss or that you arrived late for, or you'd just like to go back and watch again, then we will make a recorded version of this available and we'll send that recording to you. That'll be in your inbox in a few days' time. We don't provide copies of the slides because what we think is important is not just what's on the slides, but also what's being said. So the whole context is important, which is why we give you a link to the video rather than a copy of the slides themselves. So if you do miss anything, just want to watch it again, just keep an eye out in your inbox and you'll get a copy of those slides, a copy of that recording very soon. Also, as a thank you to all of you who are attending live, and I can see there are still some people coming in now, as a little thank you to everyone who attends live, we'll send you a certificate of attendance. That will be in the same email. It takes us a couple of days to sort things out, so don't expect that immediately, but in the next few days, you'll get an email with a link to the recording and also to your certificate of attendance. Just our way of saying thanks. So today we are looking at, as you can see on the screen, we're looking at enhanced understanding of lithium-ion battery chemistry through isothermal calorimetry. So today we're going to learn how to gain novel insights into battery materials and cell behavior through isothermal calorimetry, allowing improved performance and lifetime prediction. Hopefully, this webinar is going to equip battery scientists, cell engineers, and pack engineers with insight into how to leverage microcalorimetric systems and battery cyclers to characterize in operando lithium-ion batteries. So the three main take-home points, by the end of this webinar, you should have learned how to perform isothermal calorimetry experiments on lithium-ion batteries, how to quantify parasitic reactions in lithium-ion cells, and you'll learn a lot more about that over the course of the next hour, and how to identify cell-level events such as lithium plating. We have two guests with you today. They have pre-recorded their presentations, but then will be live with us at the end of those presentations. The first speaking guest will be Vincent Chevrier, who's an advanced research specialist at 3M, a PhD in physics, postdoc in computational studies of energy materials at MIT, joined 3M in 2010, so he's been there for a little while now, focused on the optimization, production, and commercialization of silicon-based nanostructured alloys for high energy density lithium-ion batteries. So exactly the right person to talk to us about that. After Vince, we will be hearing from Larry Krauss, who's a founding researcher at Cyclical. So he, again, PhD in physical chemistry this time. He's a founding member of the experimental consulting firm Cyclical, which provides unique analytic experimental techniques for lithium battery technologies. So if there's anything you want to know about lithium batteries, you're in the right place. Now, I have to say a huge thank you to Waters. Now, Waters pioneered chromatography, mass spec, and thermal analysis innovations, serving life sciences, material scientists, and food sciences for more than 60 years. And for the last few years, they've also been working with us to bring you topics of interest and to put Chemistry World in touch with the really interesting and engaging speakers that we bring in webinars like this one. So a huge thank you to Waters for putting us on the radar for this topic and for helping us to find the right people to speak to. Now, before we go into the first presentation, we'd like to learn a little bit more about you. So what we're going to do is pop a poll up on screen, and this is our first opportunity to learn something about you as the audience. So we'll get the poll up on screen now. Here we go. So what is your main field of interest? What drew you to this webinar, having read the description on the Chemistry World page? Was it that you're interested in battery materials? Are you interested in battery design, calorimetry, or something else? And what I can do is watch as the poll results come in, and when we've had enough people vote, then we'll share it, and you can see how you compare to the rest of the audience here today. There is at least 140 of you so far, so this should be a good representative sample for those who are concerned about N numbers, and then we will see how you compare to them all. So once again, get your questions in at the bottom of the GoToWebinar box when that's on screen for you. You can get them in at any point throughout the presentation. You don't have to wait until the end. And if you have any problems seeing the recordings or interacting with the polls, anything like that, let us know and we'll do our best to solve those problems for you as quickly as we can. The recordings may be on a slightly different sound system, for example, to what you're currently hearing. So if the recordings aren't quite loud enough, you should be able to just tweak that using your normal system settings. That's I think enough time for you to vote in that poll. We'll have another poll later to learn a bit more about you. So let's close down the poll and have a look at the results, and you can see if you can find yourself in those results. So 63% are interested in battery materials, 27 in battery design, 32 in calorimetry, and just 16 of you interested in the wider fields that this topic touches on. So hopefully you can recognize yourself in all of those interests, and we will close down the poll for now. Another poll a bit later on. So that's quite enough from me. Do get those questions in throughout the presentations. We're going to go now to the recording of Vincent Chevrier's presentation, after which we'll come back for another poll, and then we'll go into Larry and then the Q&A after that. So thank you once again for joining us. Let's play the video.
Thank you, Ben, for the kind introduction. I'm delighted to be able to present today. Today we'll be talking about isothermal calorimetry for characterizing cells, but this is in the context of a number of different techniques that can be used to characterize cells, including differential scanning calorimetry and others, as shown on this slide. So to jump right in, I'll be starting with the thermodynamic principles that are used to interpret the heat coming from lithium-ion cells and cover a few examples of how that can be applied. And then I'll pass it over to Larry, who will go through calibration, setting up of the equipment, and more detailed examples where that has been applied and the studies that were performed with isothermal calorimetry. So the thermodynamic principles that underpin this method have to do with how do we interpret the heat flow that comes from lithium-ion cells. So batteries are chemical thermodynamic systems, and so we have the tools of thermodynamics to interpret the heat flow. So we have our equation with our enthalpy, our free energy, and our entropy. And the calorimeter measures changes in enthalpy. So when we have a battery, if we have a battery that's connected and we're using it, it has a voltage, and as we discharge it, the capacity of the battery is changing. And if we had a perfect battery, what would happen is that the area under this curve would correspond to the free energy. So the free energy is the maximal work that we can extract from the battery. And so voltage times capacity gives energy, and this area under the curve would correspond to the free energy. Now, if the cell was inside the calorimeter and discharging inside the calorimeter, for example, if we had a resistor across the terminals of the battery, the heat from the work would be registered by the calorimeter, and the changes in entropy in the battery would also be measured by the calorimeter. However, normally in this technique, the wires going to the battery are external to the calorimeter and are connected to a cycler, which is outside the calorimeter, and either provides the work for charging the battery or dissipates the heat from discharging the battery. And so the heat from the work, the free energy, is not measured by the calorimeter. And so for a perfect battery, the change in entropy would be the minimal heat measured. But batteries aren't perfect. And so in reality, what we end up having is there's overpotentials in cells. So the reason for an overpotential is typically internal resistance. So you can sort of think of it as friction to operating the battery. So we have our equilibrium potential, sort of the zero current potential of the cell. And when we actually use a cell, the voltage, the potential that we actually see at the terminals is depressed, is lower than the equilibrium potential. And the blue area here corresponds to the work that we can actually extract from the battery and is measured outside the calorimeter. But the area here in orange will actually be dissipated inside the calorimeter and be measured. And this area would correspond to sort of the this overpotential here times the capacity. But when we're operating the calorimeter, what we're actually measuring is heat flow, right? So watts. And so we can express this equation in terms of current. And so here we have current times overpotential, which current times voltage gives watts. So we have a power for the heat dissipated because of the overpotential. And then we have our expression for entropy expressed in terms of current, where we have the change in entropy as a function of the stoichiometry of the material, and then related to the current by the number of moles of lithium, since there's 1 electron per lithium. And so this X here corresponds to the X in the stoichiometry of the material. So as the material is being either lithiated or delithiated, this entropy is a function of the stoichiometry. So one challenge when we look at this equation is that the equilibrium potential is not necessarily known. So it may require some sort of more detailed experiments to get it, but we can sort of get around the fact that we don't necessarily know the equilibrium potential by looking at this equation over a cycle. And if we look at this equation over a cycle, what's really nice is that the entropy term cancels out, because the entropy on discharge and will be the negative of the entropy on charge, right? So we have a sign change depending on direction. And if we look over a cycle, that term cancels out, and we're left with the overpotential term. And then the nice thing with the overpotential term is that if we go over a cycle, on discharge here, it would be the area under the dashed line, and on charge, it would be the area above the dashed line. But over a cycle, we don't need to know what the value of the dashed line is. We can simply look at the potential that we measured, the voltage that we measured. And so over a full cycle, the integration of the heat measured in the calorimeter will be equal to the area here inside our voltage curve, right? So this area has units of energy. And so over a full cycle, we can now relate the heat of the calorimeter to values that we measure directly at the cycler, namely the current and the voltage of the cell. Now, if you do this experimentally, you will actually find that the heat that you measure in the calorimeter is actually a little bit higher than the calculated heat from the voltage curve. And the reason for that is that there's another source of heat in the cell. So we have the power coming from the overpotential, the power coming from the entropy changes, but we also have power coming from parasitics. So what are parasitics? Parasitics are side reactions that are not desired and not reversible, that are happening in our cell. And so we have the lithium going between the electrodes, and sometimes there's reactions where the lithium reacts with components in our battery and becomes trapped in the reaction products and is no longer available for cycling, right? So it can no longer be charged and discharged reversibly. And each one of those reactions has an enthalpy of reaction, and so will release heat when it occurs, and that will get measured by the calorimeter. So now, if we reconsider what we actually measure, we would have the heat measured by the calorimeter integrated over a cycle. We'd have the overpotential heat measured by the cycler, and then we have this extra term, and this corresponds to the parasitics. And so rearranging this equation, we can see that we can measure we can now have a method for measuring the parasitics of the cell. So if I cycle my cell and I measure the heat from the calorimeter, and while I'm measuring the heat from the calorimeter, I also look at my current and voltage from my cycler, I can integrate these, subtract them, and what's left over is my parasitics. So I have a quantitative way of measuring side reactions in my cell. And side reactions, parasitics, are typically what kills a cell because they rob the cell from reversible lithium. And it's been shown that the parasitics have a very strong correlation with lifetime in cells, right? So measuring the parasitics can help you distinguish between the quality of cells, can help you predict lifetime. So here I've been showing you sort of this equation set over a full cycle, but it doesn't necessarily have to be a cycle over the full range. The validity of these equations doesn't require you to cover the full cycle of the cell. This cycle can be a much shorter cycle. So you could do narrow cycles over limited voltage ranges, sort of within your normal voltage range. And these equations will still hold. And the reason why this would be interesting to do is because you might be interested in parasitics in one voltage range compared to parasitics in a different voltage range. So if you were to apply this methodology, you could get a sense of what are my parasitics at different voltage ranges. And where that could be useful, so an obvious example would be in the automotive context, for example, how high do I want to actually cycle my cell? What should be my upper voltage cutoff, for example, in the field? So I can do a full cycle, I can do a narrow cycle, but if I know that my cell is truly reversible and I'm confident that the state of charge, the stoichiometry, is identical on lithiation and delithiations, on discharge and charge, then I can sort of consider the limit as the cycle gets narrower and narrower. So let me explain what I mean by that. Is if I'm charging and discharging, so let's say I'm following this path on discharge and this path on charge, if I'm confident that at this point the X in my material is the same, that I have the same state of charge here as I have here, then I can say that at that exact point my entropy term cancels. That if I average them, my entropy term cancels because one will have a negative sign, one will have a positive sign. And furthermore, I have to assume that I'm following the same path in sort of an energy space, in composition space. But if I can confidently say this, then the instantaneous entropy term cancels, and I can take the average of my calorimeter signal on discharge and on charge, and I can take this delta in voltage, this voltage hysteresis, and say that half of it will correspond to the overpotential, and subtract that. So this would basically correspond to the overpotential power. So the entropy power has canceled out. I can compensate for the overpotential power, and the only thing that's left is now the parasitic power. So now I can get a measure of parasitic power continuously throughout my state of charge. And then this gives me an even stronger sort of handle on what are the acceptable ranges for cycling, or where does my particular additive decompose. So we've seen sort of taking it full cycle, narrow cycle, instantaneous point in state of charge. And if we want to take it even a step further and sort of completely characterize the functional form of the heat flow coming from the calorimeter, we can do that in certain circumstances by noticing that the overpotential is typically a function of current. So typically the overpotential is caused by internal resistance, and so the overpotential, V equals IR, the overpotential will be a function of the current times the resistance. And if I substitute this into my equation, I get an I squared here times internal resistance. And so I can notice that I have a second order polynomial in terms of current corresponding to my heat, right? So I have second order here, linear term here, and then I have a constant that's independent of current. And this will apply in some situations where I have a very sort of well-behaved cell. And if I do have that, I can cycle my cell at different currents and basically extract the function and fit this equation and extract the functional form of the complete functional form of my heat flow coming from my calorimeter, and then get a quantitative measure of internal resistance, entropy, and parasitics. And the reference here sort of gives an example of that. So all these equations up to now have been sort of focused on parasitics. I've been focused on basically what would be useful for would be sort of characterizing cells and distinguishing them in terms of lifetime and in terms of quality. But calorimetry can be used for many other things as well. So for example, in the area of heat management, the parasitic heat flow is actually very small compared to the overall heat from the cell, and from the perspective of heat management can be essentially neglected. But there's a quantity that we can calculate that's very useful from the perspective of heat management, and that's the enthalpy potential. And so if I take the heat from my calorimeter and I divide it by the current that's running through my cell, and I subtract that from my voltage, what I get is an enthalpy potential. And what's really interesting about the enthalpy potential is that it's current independent. And so here in this cell, I have silicon being cycled at different rates. And we can see that the potential varies, the potential window opens up as the rate goes higher. And I can see that the enthalpy potential that I've calculated from the heat, so in this bottom panel here, we have the power from the calorimeter. But if I use the potential and the heat from the calorimeter, and I can calculate the enthalpy potential, we can see that both on charge and discharge at all currents, it lies on top of each other, right? So we have a constant enthalpy potential that's current independent. And once I have that curve for my chemistry, for my cell, I can back calculate the heat that my cell will produce in any cycling condition, right? So I'll have the current from the current and the voltage from my cycler, and then with the enthalpy potential, I can make a very good estimation of what the heat from my cell will be, and that could be very useful, for example, in pack design, for a given application, and from the perspective of thermal management. Another thing that can be done with the isothermal calorimetry is looking at really at the details of what's happening at the material level. So often there'll be entropy changes in a material that will give you signatures in your heat flow. An example of this is lithium plating. When graphite is filled, as its voltage drops towards zero, what's happening is all the layers in the graphite get filled and all the lattice positions are occupied by lithiums. And as this happens, the entropy drops, right? So when I place my final lithium atom, there's no more configurational states available to me, and so my entropy is dropping. And then when I start plating, my entropy becomes constant. So in the calorimeter, what I'm measuring is the derivative with respect to stoichiometry of the entropy. And what happens is I have this rapidly varying entropy, then suddenly becomes flat, and that shows up as a peak in my heat flow. And so lithium plating will have a signature in the calorimeter, and lithium plating is often a source of failure in cells, and it's also very difficult to measure. This is one of the only ways that you can sort of detect lithium plating in situ without having to take apart the cell. Another thing that we can look at is phase changes. So we can get really interesting heat signatures from phase changes. So for example, here in silicon, a really interesting behavior with silicon is that silicon is amorphous on lithiation. So along here we have amorphous lithium silicon, and we know from X-ray diffraction that right here there's this tiny little feature that's barely noticeable. You probably wouldn't notice if you weren't looking for it in the voltage curve. That happens when lithium silicon crystallizes to lithium 15 silicon 4. But if you look at the power, although it's fairly constant here, there's this huge peak that shows up because of the crystallization, right? So although it's barely noticeable in the coulometry, the current and voltage, you had this huge signature in the calorimetry. And this type of thought process of looking at material phase changes can also be looked at in terms of is my material reversible? So in this paper, the authors used my isothermal calorimetry to understand the changes in a material, and were able to identify that in this voltage curve, in this region of the cycling, they had a reversible process that was basically intercalation, and here they had structural changes in their material, and they were able to tell this by the changes in the potential versus the changes in the enthalpy potential. So isothermal calorimetry can be used to understand parasitics, to sort of rank cells. It can be useful for heat management. It can be useful for battery design. And we'd be really interested to know what application is the most of interest to this audience. And now I'll hand it over to Larry, who will walk us through some the nitty-gritty of setting up the instrument and actually making those measurements.
Before we go to Larry, though, we're going to find out a little bit more about you, our audience. So that was Vincent's presentation. Vincent Chevrier, Advanced Research Specialist at 3M. He'll be with us in a few minutes to take your questions on. Little reminder, you can get questions in down at the bottom of the GoToWebinar panel. So that's the right place to go to do that. And we've already had some great questions, so do keep them coming in and we'll make sure that we do our best to get through as many as possible after Larry's presentation. But first, a little bit more about you. So let's run our second poll for the day. What do you want to learn from combined coulometry and calorimetry? So would you be interested in the quantification of parasitics, the characterization of thermal properties at the cell level, characterization of thermal properties at the material level? We've clearly already talked a little bit about that. And the identification of lithium plating or other system level events, or is it something else? Now, this may seem like quite a specific question, but it's really useful not only for Waters so that they know what to develop and what to get in touch with you about, but also for us to know what future webinars to run, what sorts of topics would be useful to cover. And I should say, if there's something that you'd like to know more about that one of our partners like Waters would be able to help you with, then do drop us a line, cwwebinars@rsc.org or chemistryworld@rsc.org. Either of those can be used to let us know, get in touch and let us know what you'd like to know more about. We're always keen to make sure that the sorts of things we're doing in webinars really represent what the chemistry community want to learn about. So let's have a look and see how many people have voted. Over half of you voted. We've got quite a few more people in than we had earlier, so an even bigger N number for those who care about such things. We'll give the poll another few seconds to run, I think, and then we will close it down. And once again, you can see how you fit in with the rest of today's audience because you can see the full results. I think that's probably enough. Let's see those results. So there we go, 36% quantification of parasitics. And we've already had a couple of questions about parasitics. It's clearly something that's very important, very interesting to you guys. 47% interested in thermal properties at the cell level, but 54% at the level of the material. 40% of you interested in the lithium plating that we've just looked a little bit out, but again, any specific questions, get them in, we'll put them to our speakers at the end. And 12% of you are interested in the wider issues that we are addressing today and that can be addressed by these sorts of techniques. Thank you very much for filling in the poll. That will definitely help us choose the questions. It will definitely help us organize future events to try and answer the questions that you have and the topics that you're interested in. So we'll close that down for now. The next thing we have is Larry Krause's presentation. As I said earlier, Larry was one of the founding members of the experimental consulting firm Cyclical. He looks at and uses these techniques to understand better battery technologies and to help people develop new and better lithium battery technologies. So we'll hand over to Larry's presentation now, after which we'll come to the Q&A session to keep those questions coming in. I'll speak to you again in a minute.
So Vincent has provided you with the thermodynamic as well as mathematical tools that we use to practice such technique. And what I'm going to do is get into the nuts and bolts of how these experiments take place, what's important in the experiments, and then go through some examples of how we've used isothermal microcalorimeter to explore battery chemistry. So I'm going to first talk about the calibration, setting a baseline, and the equipment modifications that may or may not be necessary. We use 20 milliliter axial calorimeters, and they're very well suited for electrode and material and electrolyte characterization. This slide shows the equipment that we use. It's an older TAM3 equipped with 12 20 milliliter calorimeters with a fixed reference. We use Keithley 2602B current source meters for our electrochemistry, and this provides us with coulombic efficiency precision in the plus or minus 0.02 range. Lifter wire modifications. So over here, I'm showing our lifter, and I understand that TA now is providing a wired lifter for such calorimeters, but when we started this work, that wasn't possible. So what we had to do is modify our equipment, and we did that by punching holes, drilling holes in the thermal shunts, There's a thermal shunt here, here, and here, wires to the top. And so this is the most important thermal shunt. And we drilled holes in that and then extended our wires down into the sample area. The sample then is contained inside of the stainless steel ampule. Importantly, it's critical to seal this particular shunt from any influence that you might see from HVAC equipment. If there's any possibility of airflow through that thermal shunt, the stability of your thermal power signal will be very much compromised. So we use 4-wire configuration to do our measurements, and this is critical for all the applications that we're going to talk about here. It has to be a 4-wire configuration. And we use copper phosphor bronze alloy wire. It's low thermal conductivity wire. It's double braided. Each strand is approximately 32 AWG average wire gauge thickness. We use the double-stranded copper phosphor bronze alloy for both the sense and the current wires. In the past, and it may be useful for certain applications to use a higher gauge, thicker wire for carrying the current to eliminate intrinsic resistive heating at the wire currents, at higher currents. What I mean by that is for example, the 4-wire configuration can compensate for the voltage drop down the wires, but those wires are also going to carry current. And if your current is high enough, the wires themselves can start to produce a thermal power and then result in a extraneous source of thermal power that's not coming from your battery. And we'll show you how to determine that. And the sample, again, as I said, is placed inside the stainless steel ampule. All right, calibration and baseline setting with a wired calibration cell. Again, this slide is meant to imply that inside our calorimeter now we have a calibration cell. So for every type of cell we've used, coin cell, pouch cell, or cylindrically wound can cell, we have calibration cells which consist of the chemistry of the materials that exist in the cell we're going to do experiments on, but it does not have any electrolyte. So the cell is electrochemically dead. In the cell is placed a known resistor connected to the positive and negative so that it's actually shorted through this resistor. And this allows us to apply a current to it. So the first thing we do is after the calibration cell is inserted, we allow approximately overnight for a stable thermal power to do thermal equilibrium overnight. We then do an internal machine calibration, and that sets a gain and a baseline. After that internal machine calibration is finished and we're back to a stable thermal power, we'll then apply a constant current to the known calibration resistor to approximate a thermal power of where we're going to work in the real experiments. So that constant current then is applied for a few hours until we get a stable thermal power from the calorimeter. And after that thermal power is stabilized, we'll then adjust the gain through the device tab to equal the calculated thermal power. And the calculated thermal power, of course, is the current times the voltage. And that typically tweaks the internal gain calibration constant a little bit. So the internal gain calibration is pretty much the bulk of the calibrations, but it's very important to do that tweaking of the thermal power to arrive at a very accurate gain calibration constant. All right, when we do that type of procedure, these are the type of results you can expect. And this is from 2325 coin cells. On the left here is a plot of the thermal power versus the time at open circuit. It's just the calibration cell. And you can see the calorimeter can provide very stable thermal power, well less than a microwatt for approximately 2 hours. And on the right here is a plot of the measured thermal power versus the applied thermal power coming from the calibration resistor. For larger cells, this is for a 14200 cylindrical cell. It's approximately a 1/3 AA. wired with double-stranded copper phosphor bronze wire for both the sense and current. This is a cell that's approximately 100 times higher capacity than the coin cell. And on the left here, we see the calculated thermal power versus the measured thermal power after calibration. And we can arrive at some pretty high thermal powers. Typically, we're working more down in this range. On the right here is a plot of the calculated resistance. And on the right-hand axis here is the percent error. Typically, for a lot of our experiments lately, we're working in the 20 milliamp range. And that's the area that we tend to calibrate in. And you can see we get pretty decent accuracy of the thermal power going through that calibration. All right, open circuit measurements. And I'm not going to say much about this because the viability of open circuit measurements, while well established, they're difficult to develop electrolyte chemistry modifications that can change your cycle life or calendar life performance decidedly using open circuit measurements. So to move a cell cycle life from 200 cycles, for example, to 500 cycles, open circuit measurements are not going to be particularly useful. But there's plenty of literature in the existing literature for discussions about open circuit measurements. So I'm going to move on to the more recent applications. All right, characterization methods and examples. Extracting reaction parasitics, characterizing electrodes and electrolytes. Parasitics, as Vincent was talking about, are very important. They can take a cell that looks quite reversible, but only gives a few hundred cycles. And the result of those few hundred cycles, the low cycle number is a result of the parasitics. And Vincent also mentioned that these can be a small part of the total thermal signal. So it's important to understand these and to characterize them as accurately as we can. There are several ways to do that. So the examples I'm going to go through starts with what we call symmetric cells. And so what I need to do is to explain to you what a symmetric cell is. Limited lithium reservoir, so you have the same situation ideally as you do in a full cell. You have a limited amount of lithium, and the parasitics rob this lithium and consequently reduce your cycle life. Also, we only have one electrode chemistry. So for example, in a graphite, if one were interested in the parasitic cell chemistry associated with a graphite, which we'll talk about, this technique allows you to examine just the graphite electrode. So how do we make a symmetric cell? Well, we start with two coin cells. One coin cell we lithiate completely, and then we delithiate. The next coin cell, we just lithiate. So we take the lithium, put the lithium in, take it out, and in the other cell, we just leave it in. We take those two coin cells, open them up, and take the graphite electrode from one cell and match it with the graphite on the other cell. So what we end up then at the end is a coin cell with two graphite electrodes. One electrode is full of lithium, and the other electrode has no lithium in it. And all we're going to do now is rock that lithium back and forth. And here's a voltage curve of a graphite symmetric cell. You can see the charge and discharge. And notice what looks to be an odd voltage range, but it can be appreciated because you're just rocking the voltages back and forth. All right, as Vincent mentioned, this technique we use is called the integration subtraction method. And quite simply, it's just integrating the thermal signal from the calorimeter over one full cycle and subtracting from that the area under the voltage curve. And doing that operation numerically gives one the parasitic thermal power. So here is the thermal signal in black from a graphite symmetric cell. And here's the voltage curve. And if we wrap that around the switch point, we wind up with a plot like this. And that's highlighted on the next slide. This is the thermal power and voltage curve of a synthetic flake graphite symmetric cell. And you can see the symmetry involved in it, which underscores Vincent's point about having symmetry in the cell and the ability to apply this integration subtraction technique by canceling out the entropic terms. And these large features here are indeed due to entropic terms. From a plot like this, we can estimate the thermal power from overpotentials and parasitics. At this midpoint here, the two electrodes are exactly the same state of charge. And if there were no thermal parasitics, it would be zero heat flow, but there are some. And those come from the polarization, which can be arrived at by the overpotential associated with this hysteresis between the charge and discharge, and the remainder being due to the thermal parasitics. So we're here at this cross point of just over 30 microwatts, and you can see it's well accounted for by those offsets. And the full story of this can be seen in this piece of work. All right, symmetric cells continued. So let's look at some integration subtraction methods for characterizing a couple different types of graphite and on the lithium titanate electrode. So we're going to look at symmetric cells of synthetic flake graphite, which has a surface area of 8 square meters per gram. Another graphite, which is considerably lower, 3 square meters per gram. And then the lithium titanate cell. That's a negative electrode, similar to graphite, but with a dramatically different potential. All experiments are done at 40 C and at a C/10 rate. And this story is in this reference. All right, so on the right-hand side here, you see a plot of the thermal energy, millijoules per milliamp hour, plotted against cycle number. You can see for the high surface area graphite, the thermal power, the thermal energy is considerably larger than the lower surface area. So this is a validation of what has been known, that high surface area materials generally are much more problematic in obtaining high cycle life relative to the low surface area materials, and this demonstrates that. Interestingly, the titanate electrode shows almost no thermal parasitics. Very, very difficult to measure. And there's a good reason for that. The titanate electrode has a working potential of about 1.8 volts versus metallic lithium, where the graphite electrodes get down to about 50 to 75 millivolts of metallic lithium. So the reactivity of these materials is very much a function of their operating potential, so being very, very close to metallic lithium, so very, very reducing. I've also indicated here on the right that there is the thermal data from a Mag-E half cell. So this cell here has metallic lithium in it, as well as Mag-E, the graphite. And you can see the contribution from metallic lithium, quite large in terms of its parasitics. We also back up most of these experiments with our high precision electrochemistry measurements. And you can see these are correlated very well with the thermal results. So the titanate, almost perfect Coulombic efficiency, resulting in almost perfect complete absence of thermal parasitics. All right, what else can we learn from this? If this is indeed true, then there should be a relationship between consumed and parasitic energy. All right, so from the Coulombic efficiency and this thermal energy, we can calculate what I call a composite reaction enthalpy, a sum or a weighted sum, perhaps, of all the reactions of the electrode and the electrolytes. So what I'm doing here is plotting the thermal energy versus the number of moles of lithium lost, which we can back out from the Coulombic efficiency measurements. And you can see I get a straight line. And that straight line, the slope of that line, is the composite reaction enthalpy. And as I said, it's a composite because we have more than one component in the electrolyte. And importantly, for both types of graphite, even though they have higher parasitics because of their surface area, the reaction enthalpy is calculated to be the same. And here is the reference behind that. All right, moving on. Full cells, extracting reaction parasitics, characterizing electrodes and electrolytes. So now we're moving from the symmetric cell to full cells. And these are much larger cells. We're going to use either pouch cells or 1/3 AA cylindrical cells with a nominal capacity, as shown here, about 100 times higher capacity than the coin cells. And we're going to have much higher thermal powers too. Very useful technique for developing lithium-ion electrolytes. And the objective of this work is to determine the parasitics as a function state of charge. And Vincent alluded to this earlier. The story of this work can be found here. All right, so what does the thermal power look like from a standard lithium-ion battery? So this is a graphite negative electrode with a nickel manganese cobalt 622 positive electrode. It's in a coin cell. I'm sorry, not a coin cell, but a 1/3 AA cylindrical cell, 14 millimeters in diameter and 20 millimeters long, and it's at 40 degrees C. The orange is the thermal signal from the battery, and the blue is the voltage signal. All of the features that you see in the thermal signal are entropic effects. So for example, when we charge the cell and we get to the switch point, which is right here from the thermal data, you see a sudden change in the thermal power. That's an entropy change. Okay, so if we wrap that around each other, if we wrap that around the switch point here and plot it against capacity, you get this plot here, which is reminiscent of the symmetric cells, and you can see the symmetry of the reversible heating. Full cells. All right, so this is what we did to work out the parasitics as a function of state of charge. So we're doing narrow voltage range cycling. It's artificial graphite with lithiated cobalt oxide, and the nominal capacity is 250 milliamp hours. And this is a pouch cell. Over here, you see the full voltage curve. And what we're going to do, we're going to take bite-sized pieces of this voltage curve and cycle within those bite-sized pieces. So you see one here, one here, one here, etc. So we do approximately 10 cycles in these ranges, calculate the average thermal power, and plot that against the average voltage of that segment. And more graphically, this is shown here. Here's the full voltage curve. And in this example, I'm showing you the bite-sized piece that we're going to cycle around, highlighted in dark. And you see here the full thermal signal from the battery. Here's the full voltage, the full thermal signal from the battery. And what we're cycling is just this region here. Here's the voltage region we're cycling, and here is the thermal region. Here's another segment, still another segment, and then the top of charge, the highest we've gone. Here's our thermal signal, and here's our voltage segment. Okay, so we take that data and plot it out in a parasitic thermal power format. We get the results shown here. So there's two different electrolytes here I'm showing results from. One is a base electrolyte, which is 3 parts ethylene carbonate and 7 parts ethyl methyl carbonate. And the other electrolyte is that same base electrolyte, but we've added 2 weight % vinylene chloride. What we're plotting here is the parasitic thermal power, and you can see here the thermal power from 2 cells, sister cells, for reproducibility, fidelity. And you can see without the vinylene carbonate, the parasitic thermal power gets very high. But with the 2% VC, it's well controlled. And that's backed up, of course, by plots, simultaneously acquired plots, but independent of the thermal power of the electrochemistry. So the Coulombic inefficiency, which is simply 1 minus the Coulombic efficiency. Now 2% VC is quite a standard additive to most battery electrolytes. And here's a nice demonstration of what vinylene carbonate actually provides one, an enormous change in the parasitic thermal power. All right, we're going to talk a little bit about electrodes, electrode crosstalk, etc. This is a fairly interesting subject, but we have to go into a little bit of silicon chemistry to start. All right, so there's 2 parallel or in series, if you will, stories here. A little bit about the effect of carbon dioxide, an additive to the electrolyte, on the cycle life of lithium-ion full cells that contain fairly hefty amounts of silicon. And that dovetail into the design of positive electrodes for lithium-ion cells with silicon. And it's in this piece of work where we uncover the contributions of a positive electrode to the overall cell chemistry. And to be more explicit, when you're looking at the thermal power of a lithium-ion cell, in principle, you don't know whether you're looking at the positive or negative. There are insights into that. But it's possible that the positive electrode can be contributing materials, gases that dissolve in the electrolyte and affect the performance of the negative electrode and vice versa. So that's what this story is about. But let's talk a little bit about the silicon work. All right, volume expansion of silicon leads to failure in lithium-ion cells. So the use of silicon is becoming more and more accepted in a number of different applications. And we've done a lot of work on this ourselves. And this is a bit of a story about a lithium-ion full cell, pouch cell, which has about 15 weight% of a silicon alloy. Now, it's not elemental silicon, but it's an engineered silicon. Silicon itself, when it's fully lithiated, can expand 300%, which is basically intolerable. So most efforts at including silicon have involved not elemental silicon, but an engineered type of silicon, so that the volume expansion is more akin to, say, 100%. So we have three cells. The positive and negative electrodes are all identical. We have the control, which is just ethylene carbonate, ethyl methyl carbonate, and that's the black line here. And it might be more useful to look at the normalized capacity. So here's the control. And if we take 80% of capacity being the dead point, our cell is dead, we don't even get 60 cycles out of this electrode. But if we add 10 weight% fluorinated ethylene carbonate, you can see a dramatic increase in the cycle life. And if we add a source of carbon dioxide, you can see what happens to the cell cycle life. It's dramatically different. So let's turn to the thermal power signal and the Coulombic inefficiency. So this is the thermal power signal from just the control. And you can see as we're using our integration subtraction technique and examining the state of charge up around the top of charge, 4.15 volts or so, we're up around 600 microwatts of parasitic thermal power, and that's supported by the Coulombic inefficiency. And I want to show you that same data on this slide. Here is the parasitic thermal power from the control and the Coulombic inefficiency. And I had to put this on different plots because of the change in scale. Notice what happens to the thermal power when we're using 10% fluoroethylene carbonate in our EC-EMC blend. The parasitic thermal power is just dramatically lower, and it's even lower still for the carbon dioxide additive to the electrolyte. So again, very supportive of the effect of cycle life on the parasitics that we're evolving from just the electrolyte and its impact on silicon materials. Electrode crosstalk. This is particularly interesting and very surprising. So we have two cells here, two different types of positive electrode, the same negative electrode, and it's a silicon containing a negative electrode. The first cell I want to just show you about, give you a sense of how the positive electrode can impact the cycling of the total cell and materials that can come off the positive. We have a lithiated cobalt positive electrode, and we're showing the thermal parasitics at cycle 17, which are down here. We look at it again after cycle 45, and you can see the thermal power now has evolved up to this level, quite high. And after 75 cycles, look at the thermal power now. It's almost 1.5 milliwatts from the lithiated cobalt oxide. But look at the cell that has the NMC 622. Everything's buried down in the bottom here. And this is all supported by the Coulombic inefficiency measurements. And the reason for this is that the NMC electrode is contributing carbon dioxide at the top of charge. And that impacts the overall cycle life of the battery. So an interesting example of how the positive electrode and its contribution to the evolving electrolyte chemistry cannot be ignored. All right, so a summary. The heat measurement, polarization, entropy, and parasitics can all be obtained from the use of isothermal microcalorimetry. There are many things that one can learn from isothermal calorimetry, including, well, as we talked about, the parasitics, which are something we look at primarily, entropy changes, total heat production of the cell, etc. Quantification of parasitics can guide electrolyte and cell optimization. This is a very useful application of the equipment. And the use of symmetric cells can also isolate the positive and negative, allowing independent investigation of the electrolyte chemistry. All right, that's it. There's some references that follow, but I want to thank you for your attention. Hopefully this was a good introduction to the applications of heat flow calorimetry to lithium-ion battery chemistry.
Thank you very much, everyone. So that was presentations from Larry and Vincent. I'm delighted to say that they are both with us today to answer your questions as well. So there are some details on the screen if you'd like to get in touch with Waters to find out more or follow up about this afterwards. But let's just dive into your questions now. Forgive me for looking over your shoulder. My questions are on a different screen, so I'll have to look over there to catch up with them. So let's see if we can get both Larry and Vince on camera, and let's make sure their microphones are on as well. Larry, I think we can hear you already, and Vince, we can see you, but I don't think we can hear you yet. Hopefully we'll sort that out. Well, yep, that looks good while we get that sorted. So a couple of different people have asked similar questions, so I'm going to try and wrap them up into one. Jürgen and Alexander have both asked something very similar. What are the sources of parasitics in lithium batteries?
Yeah, so that's a good question. Can I share my screen in this context?
Yeah, we can make you presenter. All I will do now is hit the button and you should get the, there you go. Yep, we've got you.
All right, and you can see my screen?
Yes.
So the origin of the parasitics is, it's pretty complicated, but basically, it's typically the formation of SEI, so the formation of reaction products on the surface of the electrodes. The reference I have on screen here in preparation for your question is a good place to start that sort of details, like what are all the possible sort of reaction pathways that can lead to SEI. That being said, this is just sort of like an entry point. The question of exactly what the reaction products are given an electrolyte is an extremely complicated question that's sort of been studied for decades. And so, but typically, you have reactions of organics and lithium, leading to lithium organics depositing on the surface of the electrode materials.
So Larry gave us a couple of examples, right? A source of CO2 or the 2% VC, a couple of things that can affect the impact of these. What other things should people be investigating, or what other things can we do to minimize the effect of parasitics on a battery lifespan?
Yeah, so there's a variety of strategies. There's the additive strategy where we change the composition of the electrolyte to either give reaction products that are more passivating or to increase the stability of the electrolyte. There's the choice of the solvents in terms of their voltage stability windows, and then there's also the whole approach of trying to coat materials to increase their stability, right? So the whole field of coating materials is both a negative and the positive. There's a fair amount of literature on that topic. I don't know if Larry wanted to add anything to that answer.
Well, not really, only that it's very unlikely that the lithium-ion battery chemistry will be absolutely 100% reversible without any energy loss. There's a lot of work going on for solid state electrolytes. Things like that could make a huge difference in the parasitics. But remember, these parasitics we're measuring are a very small percent of the total energy that the battery is actually providing, but they are essential for calendar life and cycle life.
They're certainly worth considering. We're pretty much out of time, but I think we'll see if we can squeeze an extra question in before we go. So thank you to everyone for sticking with us as we just run slightly over time. Wesley asked what the time resolution is of the technique that we're using and whether we can use it to look at things in very narrow, defined slices of time.
Yeah, so the calendar has a time resolution, basically a time constant. Maybe Larry would be best to answer that question.
Yeah, the time constant of the calorimeter typically is around 900 seconds. Of course, that's going to depend upon the characteristics of the device you're measuring. But from our perspective with parasitics, they are ubiquitous, and it's not something that we can necessarily get at exactly the same. There are issues of material flux across the interface layers that require some time. So if the question is directed towards instantaneous measurements, that is rendered rather unattainable, primarily because of the time constant of the calorimeter.
Wesley, hopefully that answers your question. I'll see if we can squeeze one more in. I'm going to ask you to gaze into your crystal balls. So Left Terrace has said that I've heard lithium-ion batteries are due to dropping costs quite dramatically. Do you think it's the sort of techniques, the sort of understanding that we're getting from these approaches that could see cheaper, longer lasting, more reliable battery technologies in the future?
Yeah, so for cells that last years, parasitics are one of the primary failure mechanisms, and this is one of the most accurate and most sensitive ways of measuring those parasitics. And if you want a cell that lasts years, then being able to measure those parasitics really accurately is really important in order to be able to make any sort of prediction. And so yes, we see this as a tool that is important, particularly for the application of cells that are meant to have very long lifetimes. And in terms of the cost of cells, I don't necessarily have a crystal ball, but yeah, I mean, we look forward to the cost of cells going down with time and their applicability growing with time.
Excellent. Thank you very much. I think we probably have pushed it longer than we really can. So thank you to everybody for sticking around as we overran by a couple of minutes. But thank you for your questions as well. And a huge thank you to Vince and Larry as well for joining us today. Obviously, your presentations were recorded so that we knew we could squeeze in all of the important detail that we wanted to get in without running out of time. So thank you for being able to join us for this Q&A to squeeze in a few questions at the end as well. So thank you very much to Vince and Larry, and to Waters for putting us in touch with them and for highlighting this as an important topic that the chemistry community was very interested in. So just a little reminder, we'll send you an email in a few days' time with a link to the recording and to your certificate as our way of saying thank you for turning up live. All I need to do now is say a huge thank you to Larry, to Vincent, to Waters again, and to all of you for attending. This has been a Chemistry World webinar. There are plenty more that you can get your teeth into, even the webinars that have happened in the past. If you have a look in particular, we've done a good series of them with Waters. If you're interested in the sorts of things that can be done with Waters technology and Waters techniques, then have a look at chemistryworld.com/webinars, where you'll find all of the webinars that we've done with Waters in the past. And of course, there's a couple coming up as well that may also pique your interest. So have a look there and let us know if there's something you'd like to register for. There is an exit survey coming up that really helps us, so really do fill that in as you leave. Thank you very much. And that's it for now. I'm Ben Valsler, Chemistry World's digital editor, and this has been a Chemistry World webinar. We'll see you for the next Chemistry World webinar. Thanks again.